Alright, so for question A, we want to derive partial derivatives for this C0 with regard to a weight. And then, well, let's just first write out this C0 in the form of the variables we're dealing with. So this C0, according to the form. So here we are not considering regularization here. It's 1 over 2 times y minus a squared, right? So y is the label, which is constant, so it's the ground truth label. And then a, it says that a is sigma z, where sigma is the activation layer. So it says here it's a differentiable nonlinear function. So the common choice of sigma is what we have covered in the class, for example, sigmoid, and also relu. They are all like nonlinear differentiable activation layer. So here is just represented with this symbol. And then z is the linear layer before it. So here it says z is wtx. And then w, we have 3 parameters. So x is also three-dimensional vectors. So we just expand this a here. It's going to be this sigma, then wtx. Square. And then just to make this make more sense, we can write it. We can think of it like this. So we have this x input. So there are a few neurons before this. So we apply this weight. So this weight is basically just a matrix that converts all of the things to a few numbers of output neurons. And then we then pass through the activational layers. And then it's going to be output. So it's first passing through the linear layer, and then pass through the activational layers. And that's basically neural networks just keep doing this too. So first linear, and then activation, and then linear activation for a node, right? And then if you want to expand this a little bit more, you can also make it expand it a little bit more. If you're not feeling like very comfortable with the form of linear algebra form. So wtx for this question is just, we have three variables, right? 3 parameters, 3 variables. So it's just w1, x1, w2, x2, and w3, x3. And then square. So the w here is just All right, so now we can look into the question. What it is asking for is what is the derivative for a weight? So what is the weight here? It's this w1, w2, and w3. So we can just look into, for example, we just look into w1 here. So what is the partial C0, partial w1? Just take the derivative. So here, there's a square outside of this. So it's first, we take the derivative of this whole part, and then there's a 1 over 2 before it. So it is exactly the same as the original thing we have here. So this thing, 1 minus, and I just write in this form because it's shorter. And then we're gonna look into the derivative of the inner part, of this part. It's within the square. So basically that's a chain rule. And then the part within it is y is a constant. So it doesn't matter about w1. So it's only this part, sigma, parenthesis, w1, x1, w2, x2, w3, x3. So it's all, again, it's a chain rule. So this sigma is a differentiable layer, as it said in the question, but it doesn't say anything about what is the exact derivative of this function. So we just write it as the general form, as partial sigma, then partial this whole part. So this whole part is just WTX, where whatever variable you want to use here. It's just a symbol here. I just write WTX, and then times WTX, partial WTX, partial W1. So what is partial WTX, partial W1? It is just X1, right? So because this is the only constant before W1, the other are also is now viewed as variables within when we were calculating the partial derivative for X W1. So here it's just X1. So and also here's a negative sign. So there's a negative sign before this. I forgot it. And I'll write it here. So basically, this is the derivative, partial derivative of C0 with regard to W1. Yes, and you can see that there's actually a symmetry within this expression. So for whatever W1, W2, W3, all you have to change is just change the number here. So we can now change this equation to partial C0, partial WI.
But
We'll just
doing the square.
Square is already canceled out.
Oh,
So you just said this equation applies to W1, W2, and W3. All you have to do is to change this, from X1 to X.
Should this be WI?
No, this should be WTX, the whole part, because it's sigma.
But you're differentiating with respect to WI.
So sigma fx, then partial sigma partial x is partial sigma partial f times partial f times partial x. So it's a chain rule. So the denominator here should be the whole form of the thing within it, not just the x itself. So this is the chain rule. Or you say that it's fg. Maybe that's what you usually use. So you say that z is f gx, then dz dx should be df dg times dg dx, but not df dx times dg dx, right?
Okay.
So that's why I said WTX here, because here this variable is this whole thing. But honestly, you can just replace this with whatever variables, because here the variable is not even like W1, W2, W3 cell. It means that this whole thing is the variable. So I can also say that this sigma is just applied to a variable z, and say that it's partial sigma partial z here.
Oh,
You see?
okay.
So here the variable is not W1, it's not the x within here. It's just the whole thing itself, and g is just a symbol for it.
Okay.
And then for the learning, the update rules. Update rule is just WI should be update to, I just write this as the update, WI minus learning rate, eta, and then times the gradient of the partial derivative of it. So it's the partial derivative of the cost function with regard to this WI, with regard to this parameters. So this is because the gradient is specifying the direction that this function increase most. And this is a cost function. So we want it to be smallest. So we want it to decrease most. We want the direction that it decrease most. So we just minus learning rate times this gradient. And this is the update rule. So you got this result from the previous equation. You just plug this into this one, and then just apply this to every weight. Or you just say that this applies to every weight. where I can be from 1 to 3.
Is this second term also the step size?
Step size, this one?
Yeah, that's step size.
Yeah, I think learning rate. Yeah, you can also call it step size. So basically, that's the step you're taking within every gradient, each gradient descent.
I just wanted to be clear. So this weight at the kth iteration equals to this weight at the k minus 1 iteration, and then this is the gradient for the k minus 1 iteration.
Yeah.
Just want to be clear.
Yeah. So this is not equal to. This is why I wrote it like
Okay,
this. This
okay,
is
I
assign.
see.
So assign this to assign the right to the left. So that is basically the equal in programming,
Okay.
right? So it's assigned, not actually equal to. And then for question